I'll share the screen. Let me know if you guys can see the screen. Um, you can see the screen, right?
Yes, I can.
Yeah. So this notebook will be uploaded to the Git, and you can run this in the Collab. And we will not run here. This will take time, right? And yeah, so we will deal with the classification tasks, and for that we'll have some helper functions, right? For on MNIST dataset, such as this just gets the data loaders, and because we have these data sets MNIST and CIFAR already present in the Torch Vision, like this data sets thing, we can directly use the inbuilt data sets functions and data loader functions to get this. If you have a custom data, we may have to work little hard to build these data loaders. So for now, we don't consider those things because that's not important at this point. And similarly, these are definitions for getting CIFAR10 data loaders. Again, the CIFAR10 dataset is present in the Torch Vision. And yeah, we get train, validation, and test datasets. And this is for setting the seeds to replicate the experiments. And this is for computing the accuracy, and this is the confusion matrix. Okay, so we'll go through this function in detail because this is where the actual training is happening. So this is something we need to specify how many number of epochs we need, and train model takes the function model that you are training. As can be a ResNet or VGG or any network, right? And this is a number of epochs, and this is remember the train loaders that we have obtained, that we have to obtain using the helper functions, validation and test loaders and optimizer, any SGD, Atom or Momentum, any optimizer. And this is device, like if you have GPU, pass the CUDA colon the GPU ID, or if it's not, it takes CPU. And this is logs the results for every 50 intervals. And yeah, so this is the loop over epochs, right? We specify a number of epochs to train, and now here we assign model to train, right? uh, so model.train, what it will do is it assigns the model in a training mode. And one thing to be to be aware is the way training and model.train and model.eval differences happens only for the layers which behave differently during the train and test. So anyone have idea which layers of the neural network behaves differently from train and test?
Dropout and batch normalization.
Great, right? So dropout and batch normalization. So if you have this dropout and batch normalization in your neural networks, you need to be very careful while doing these operations. We need to do this. If we don't do, we'll get unexpected results. So model.train keeps the buffers of batch normalization active, and you keep updating as you pass the data, as you keep doing the forward pass. And same for dropout, it keeps doing the on and off of the neurons. Okay, and yeah, so this is a typical syntax for enumerating train loader, right? This gives you the index, and this gives you the features and targets. And now once you get this, you need to store this to what device we want, right? We pass this to a GPU, pass this to CPU. This is just .2 of device. Now this we get the logits once we pass the model to features. I mean the not features, yeah, input basically. And once we get the logits, and we use the torch.nn functional cross entropy to find the cross entropy loss. And first is the logits, and this is targets. So what are these logits? Are these softmax operated logits or without softmax?
Without softmax.
Right, it's without softmax, yeah. And we need to zero out the grads using this command, because the nodes in your computation graph may have some gradients already present, right? And so before applying your loss dot backward, we would like to clean them up, right? So this is the point, loss dot backward, where the actual gradient computation of the parameters of the network with respect to loss happens. Okay, it happens, but the gradients are not yet applied. Okay, where the gradients are applied are this is the step, right? Optimizer dot step. Now depending upon the optimizer, this is your momentum, SGD, ADAM, accordingly this optimizer will keep updating the weights, right? If it is ADAM, it maintains the states, right? The first order gradients, and the second that you have these norms, right? It keep maintains the state. Okay, so that's it. So you keep appending the loss here, and once your this thing is done for given epoch, it runs through the entire training data. Okay, for every epoch. Once that is done, we set this to eval mode. Eval mode is where we use to we want the model to do inference, right? Now always remember, in the eval mode we always want to evaluate in no grad mode. Okay, so you want to save the memory, otherwise it keeps creating this placeholders for computing gradients and all. Okay, during inference always remember to keep this evaluation within torch.nograd. Right, you just pass the model and try and pass the train loader and the device and get the accuracy of training and validation. Okay, so that's the thing, right? That's how this is the main loop for training any deep learning model. And for this we need a model to train, and we need a training data and validation data, test data, of course, which are in the form of here train loader, validation loader, test loader that we have seen earlier. So any questions so far? And yeah, we need some functions to plot that you can go over. That's not the point here. Okay, so yeah, so we'll see the this thing, right? Here we are creating the model, the ResNet 34 model. Okay, and yeah, so here once we create this model, the ResNet model, by specifying this number of class and layers. So actually, let me see. Yeah, this is the ResNet, the original paper of ResNet, right? So this is the ResNet 34, right? Here the 3 and 6, right? is that 3463, right? So 3 represents this thing. Okay, these two con blocks, this thing is there, right? Resonate block that represent 1, 2, 3. Similarly 1, 2, 3, 4, right? Similarly 6, 1, 2, 3, 4, 5, 6, and then 1, 2, 3. Okay, so this is what the configuration represents, right? Once you specify this, the code internally creates that ResNet architecture. Any idea? Any questions on this? What does this 3463 mean?
I think, are you using a for loop to create this layer?
Yeah. Code
Okay, okay.
is little bit involved, right?
Hmm.
So you have to go through each and every line, and it is worth thing. Once I upload it, you can go through the this thing and match it with the original paper of
Okay,
ResNet.
okay.
It's present in the internet. Okay.
Yeah.
Yeah. The key thing is I just wanted to show like what does this 3463 mean. And yeah, optimizer, scheduler is typically, right, you schedule your learning rate. Typically we would like to decrease the learning rate over the time, because as you keep reaching the minimum point, you don't want to overshoot your step, right? That's the advantage of this, reducing the learning rate. And once you create model, once you have optimizer, and once you have data loaders, right, that just call the train model as we have discussed that already. And yeah, that's it. So once you train this, we can plot it, right? So that's what we have done. I think it's ran for, I think, probably uh, 5 epochs. Okay, and this is on CIFAR 10, and we get an accuracy of 55.5. And you can see the training loss, and yeah, this is just training and loss basically. And this is the validation accuracy. Okay, and we would like to visualize the data points. I mean, how the CIFAR 10 classes look like, right? Cat, sheep, plane, frog, you know, automobiles, trucks, horse.
Can you answer one query of mine?
Yeah, please.
Yeah, like I wanted to understand why are we feeding these blurred images, like not why high resolution images into this model? Like, that is one question I have.
That's just the choice of the data set. This is 32 cross 32. The data set itself is like that.
Okay.
This is 32 cross 32. Data set by default, it is like this. CIFAR 10 and CIFAR 100, it has 100 classes. They are like this.
Okay, got it.
Yeah, if you go for ImageNet, it has a better views, like 224 cross 224. But then runtime will be tremendously high for ImageNet.
Yeah,
You can
yes,
understand the
obviously.
processing of such a huge images, right? And with the kind of GPUs we can sort of afford, right? ImageNet training, let's say on VGG, it takes several days, several weeks probably. And yeah, so another part is fine tuning CNN. So far now here we have seen this thing. It was training from scratch, right? You can see the accuracy, right? It's going from 13, 27, 39, 56, right? So another thing, typically it's a norm actually. Whenever you want to train a CNN, PyTorch has so many models which are trained on the ImageNet, and the weights are stored. So whenever you load a model and we need to specify pre-trained is equal to true, then it loads the ImageNet pre-trained model. So it serves as a very good starting point for so many downstream tasks, right? It has become a norm. Like we never start anything from scratch. Typically we always do fine tuning. Again, same set of functions here. The only difference here being that I'll show the pre-trained. Okay, so here we use the VGG model. Okay, and yeah, so now we have created ResNet as we have seen, and now here we are loading a VGG16 model. Right, when we say pre-trained is equal to true, it loads VGG16 architecture, but the weights are those weights where we have trained the VGG16 on the ImageNet. So it gives you a very
Hello,
stronger
can't hear you.
starting. Hello, can you hear me? Can you hear me? Hello, can you hear me? Hello, can you hear me? Can you hear me? Hello,
Hello, yeah. I think I got disconnected, I guess. Over.
can you hear me
Yeah, I can hear
now?
you now. Yes. Yeah, I
Yeah,
can hear
okay,
now.
okay, okay. Yeah, what I was telling was this thing. Um, yeah, so it's always a norm that we use a pre-trained model for downstream tasks. So in this, we are using a VGG16 pre-trained model. This pre-training happened on ImageNet data. Okay, and this is once you print the model, it gives you what are all things present in VGG. Now, how do we freeze the model? And how do we selectively want certain weights of the model to be trainable or not, right? So they can um, uh, you can for this command especially, right, uh, it iterates over all the parameters in the model, and there you can set every parameter to be false. If you want to selectively uh, make some parameters to be true and false, here you can write name comma param in model dot named underscore parameters, and if you know the name, you put a check if check on the name, and then selectively um, set the gradient to be true or false. Okay, and yeah, that's it. So once you have this pre-trained thing to be true, and so here they have set all the initially they made all the parameters to be false, and they have chosen particular set of the last three layers to be true. That's it. So in the VGG net, the last three layers, right? This three linear layers. This one, this one, and this one to be are set to be true, and everything else is frozen. That is taken from ImageNet. Okay, that's what fine tuning means, right? You just tune the selected layers. Okay,
Okay.
so yeah,
I got one question. So I get
yeah.
confused between fine tuning and transfer learning. I know like they are same. So
Yeah, sort of same only. Yeah.
they are same. So like, is it like in transfer learning, I freeze the weights and then train the little layers for classification? And whereas for fine tuning, is it that I start with, like, for example, I already have a trained model. So my starting point for like I retrain these weights, right? I have a pre set of trained weights, and I like not don't I do not freeze them. Is it like that?
Frankly, but they both are same to my knowledge. And whenever you do transfer learning, you have something uh, uh, to begin with, and that you are transferring to your downstream task.
Mhm.
Yeah, fine tuning is also the same thing. You have you have a model, and you
Mhm.
don't want to update the entire model. You just want to update certain layers of a model, but it makes sense only when you have a better initial starting point. That better initial point is nothing but a pre-trained model. So yeah, to me, I mean, they both are same.
Yeah.
Okay. Yeah, you can see, right? The accuracy here starts with 72. There we had started with 13% when you're starting from the scratch. Okay. Yeah. This is just a confusion matrix. And so here it just means that, our aeroplane is predicted as truck 16 times and ship as 56 times and horse as 9 times. It predicted aeroplane as aeroplane most of the time, 726 times. That's what it means. And yeah, so it's clear, right? How this how to use the torch to train a model. And so important thing is we need the model creation and data loaders and data sets. Once we have these three, we can follow the same template of training the code as we have gone through the train model function. Right? These three will keep changing uh, from data set to data set. Okay. Any questions? No. If no, I think we can go to the simple problem solving sessions today.
Yeah, fine. That would be nice.
Okay. Yeah. Yeah. Can you see the screen?
Yes.
Yeah. So this is just a very quick overview, like how CNN has evolved over time. So initially we had Linet for digit classification and all. Then 2012 was the AlexNet, where it has shown massive improvement on the ImageNet challenge. Then we had VGG, and then followed by ResNet. So ResNet is the state of the art, CNN. And now this are replaced by vision transformers, I think, which we will discuss going forward. Okay, so why resonators are so popular is because they employ something called as residual connections, which allows the gradients to flow deep into the network without getting vanished. Okay, there are two series for ResNet architectures. So ResNet 18 series and ResNet 20 series. So one question is, which of is ResNet 18 has more parameters, ResNet 20 has more parameters?
I think 20. I don't remember it exactly.
Yeah, it's ResNet 18 actually. ResNet 20 is specially designed for CIFAR kind of data sets. Okay, it's much parameter space of ResNet 20 is much smaller than ResNet 18. You can go over the ResNet paper actually. Maybe I think after
So it
solving, I just go over those details.
so 18 means number of layers, right? 18, 20 layers, 18.
Is number of layers, yes. 20 means number of layers. So even though 20 is more deep than 18, but 20 has much smaller parameters.
Okay.
Okay. And yeah, let's go over today's questions. So which of the following statements are true about resonant architecture? Right? You can take time and try to answer. That would be better. I instead of I reading, the answers. So today there won't be any math kind of questions. It's all most of the questions is based on the architecture. So it will be like this: why and how, those kind of things.
I think option 2 is correct.
Option 2 is correct. Yes.
Okay, multiples can be correct, right? Then 1 and 2.
Right. So 1 and 2 is correct, and 3 is obviously wrong. Right. It works for deep architecture. That's the key motivation for introducing this resonance. And using skip connection requires extra parameters? No, it just requires adding this thing. Okay. And
Residual connection and skip connection, they mean the same thing, right?
exactly, yeah, they mean the same thing. It can require, we need to be careful here, because if my okay, let me show you this thing. Let me Sketchpad online. I mean,
So
in
skip
general,
connection is, yeah, please, you go ahead. Yes.
in general, I mean, the answer should be no. I mean, it doesn't require more parameters, but here is this thing, right? This is how we are doing the resonant thing. Take this guy here and add it here, right? This is the residual block, right? This is the skip connection. The point is you need more parameters only if the dimension here and dimension here are different. Okay. Because you may need one more parameters here to make this dimensionality similar to here, this thing. Okay. So that's one caveat. Okay. You may require, but yeah, I mean,
So
I
one question. So for skip connection, we use identity matrix. So if we choose not to use
identity
identity matrix,
correct. If you're not intended to use identity matrix, you need more parameters. Again, if the image, say here we have got say 16 cross 16 image, right, after passing through the layers. But initially, if my image had say 24 cross 24, yeah, I mean, not image activations, let us say, you can't add these two, right?
no.
Yeah, so there we need some matrix W that downsizes this to 16 cross 16. It can be
So
trainable. Yeah.
so can you tell me, if we choose not to use identity matrix, then what kind of what kind of other thing we can use? Like, do you have any
Any
idea?
trainable matrix we can use such that you can
Okay.
reduce the space from 24 to 24 to 16 cross 16. So it is already mentioned in the actual resonant paper. Okay, so you can use this thing. Say, ideally, want you will add this x to this, but if x is not of same dimension of this thing, after applying resonant operations, you can have some projection layer that brings to this dimension. Okay.
Okay.
Yeah.
Yeah.
And yeah, so I think that's first question was fine, right? It's true, right? Yeah, A and B are correct. And yeah, so what is the need for one cross one convolution? I mean, it was, I think, introduced in this inception nets, right?
3.
3 is true. Yeah, 3 is true. Agreed. Yeah. And yeah, 2 is also, you can say it's fine. I mean, it's true.
Yeah, true was also looking good to me,
Yeah.
but I was confused between
Yeah,
2
I
and
mean,
3.
these are a bit. I mean, it's not. That's what, right? It's not a math question. It's a bang on. If it's there, it's there. Right? It's not there. It's not there. This is, you need to choose the closest things, right? So it's 2 and 3 are correct. And yeah, so GradCam, as have you guys familiar with GradCam?
Yes, but I forgot about it now. I don't
No, no,
remember
no.
it
In
right.
the lecture, in the lectures, it has been taught, this week's
Yes,
lectures.
yeah, yeah, it
Okay,
was.
okay, okay. So what are the typical properties of the GradCam? Uh, it says, first option says it does not assign unequal weights to different pixel gradients when computing activation maps. I mean, this is false. You want to assign different weights to different pixels, right? To see where the influence is happening, why we are predicting something as something. Okay, and the pixel wise gradients can be computed without calculating the gradients. This is false,
False.
right? And it does not require additional training. That's true. Yeah, we don't need any data to train things. And it enhances positive gradients of class activation scores. Yes, it is true. And it works well on object localization. Yes, it works well on object localization, 3D action recognition and other such tasks. This I'm not sure, but yeah, it works well on object localization. Yeah, so CDE are true. Which of the following principles are obeyed by efficient nets? It relies on compounding
One,
scale of depth, width, resolution. Yes, and the general principle of model scaling can also be applied to mobile nets and ResNets. Think so. Yes, and it helps architectures to achieve maximum accuracy under given budget of resource constraints. Yes, I don't think so. This is fourth is true. They take long time to train. Yeah, and yeah, which of the T-SNE plots you guys are aware,
yes.
right? So basically, what is the difference between T-SNE plots and the PCA based things? Any idea?
I know that both are used for dimensionality reduction, but underlying mechanics I don't know for TSNE.
Okay, I think I can quickly go over the TSNE thing. Um, so computing, basically TSNE is, you can visualize non-linear way of reducing the bringing down the dimensionality thing, and PCI is sort of linear. Okay,
Yeah.
and so computing TSNE plot does not involve optimization. That is not true. There is an optimization, specific optimization problem that TSNE or just SNE solves, and it involves comparing the Wasserstein to distance between a Gaussian and heavy-tailed student distribution. No, it's not Wasserstein distance. What we compute is the KL divergence. Um, Visual clusters obtained are from using the method are independent of any parameters. It's probably true.
So one question, KL
Yeah,
divergence is used to measure the distance between two probability distributions. And what is this?
not
What's
distance,
this?
not distance. It is divergence.
Okay, divergence. And what is this? What's a sustain distance?
It is all. It is some kind of. It is also some kind of distance. We will go through it, I think, in detail when we discuss probably Wasserstein GANs, if at all it's there. If it's not there, I think I'll make a note of it and I'll discuss in detail next week. It is a distance between the two, same thing, right? Between the two distributions. Um, It's different from KL divergence. Yeah, I'll discuss this in the next week in detail if you want.
Okay, sure.
But yeah, this is in our context. I think we may encounter this going forward in the GAN series where we discuss Wasserstein GAN. If we discuss. Okay, so using a heavy tail distribution alleviates the crowding problem. This is true. So basically, crowding problem is, I mean, what happens in this crowding problem is, um, so if we have in higher dimensions, right, we have some point and there are some close by points, let us say, and say we have 10-dimensional space, and so we can accommodate say 10 points in that space which are sort of equidistant to a given point, right? And now to represent those things in a low dimensional space, say from 10 to 2, because we want to visualize in 2 dimensions, right? When we bring it down from 10 dimensions to 2 dimensions, it will be hard for us to maintain. I mean, we can't put 10 points in 2 dimensions and maintain sort of similar properties of higher dimensions, right? So that creates something called as uh, crowding problem, basically, right? um, because we can't have probably, I think, 10 points in 2D which are equidistant from each other. So yeah, one way to avoid that, uh, so SNE uses just the distances. So they call something called as T-SNE, T student neighbor, and it uses imposes a distribution in low dimensional space that has long tail, and it is claimed in the paper that this will reduce this crowding problem, sort of deals with crowding problem. Okay, so this is about it. Yeah, so any questions on this?
I need to like study this because I did not look into it before. I only knew about it.
Yeah, so it is this paper. Okay, quite a influential paper.
Do you
I
have any tips how
suggest.
to read papers? Because papers can be very very heavy, very very theoretical.
um I mean, it's not that difficult, this paper especially. um okay, so let me go through this thing, right? So the way they assign, let's say we have some n data points, right? What is this saying is the similarity of data point j to data point I is modeled as some probability, right? So similarity that j assigns to I is nothing but the distance between, you just evaluate the distance between I and j. I mean, this is like a Gaussian kernel, okay? And sum across all the points that doesn't include j. Sorry, that doesn't include I here, right? That's the um, what should I say? Similarity that j is to I, right? That's what it is, right? Yeah, data point xj to xi. So that's how they define this, and this is an n-dimensional space, right? A higher dimensional space. Now this y is very low dimensional space. So the property that we wanted is these distances, how they behave in higher dimensional space, we want the same similar thing to happen in lower dimensional space, and we convert these distances to probabilities, p's and q's. Once we convert, we have some divergence measure in the probability space, KL divergence, and we apply KL divergence to minimize this.
Uh, One question. So that
Yeah,
P probability that is in higher dimension, right?
this one, yeah, p is in high, q is in low.
Okay. So now there is my question. So how can we measure distance between two different dimensions? Like, is it even possible?
No, we are not measuring between two distance. So this is a number. So the point is,
Okay.
the points in high dimensions, how they behave, they should, if I bring them back to low dimensions, they should behave among themselves similarly in terms of distances. So y's are low dimension things, right? They are the
Okay.
distance computation is among themselves. It's not between y and
Okay.
x. Never, it was never between y and x. Okay.
Okay. Then it makes sense.
Okay. Yeah, so that's it. And so when they do this, this is called as SNE. SNE encounters some problems such as crowding problem. Okay, and they introduce something called as T stochastic neighborhood embedding, and I think they discuss in detail about this crowding problem. Yeah, here we can go through this. It is very interesting paper. You can spend time on this and resonates. I think that's what I have shown today. Right. Yeah, I think that's all I have to say. Um, okay. Anything else? Any questions that I can answer?
Yeah, uh, it is actually about the course. So, in the final examination, like what kind of questions can you expect? Because the thing is, the course is very good, but like the depth is too much, and also like I'm working in a full-time job, so I have to manage both them side by side. So, in the final examination, what kind of questions are we expected? Like, because this is fully math based. So, are
No,
we
no, no.
expected
I
to?
mean, I don't think so. This is fully math based. It is to some extent math based. I agree. So now I think the math part that comes heavily is GANs and probably diffusion models and basically variational autoencoders, the generative part of this thing, right? We need a lot of probability things, but I don't know. I mean, and this course keeps upgrading every year, right? Because the new trends are coming in into the deep learning, right? So all these are sort of accommodated over the year. It is being, I mean, across the time, keeps on improving, and that is good. Yeah, I think it's worth spending effort on this. I mean, uh, forget, I mean, the exam, but I think it's worth doing
Definitely
this.
the course is enjoyable. Like I learned many
Yeah.
things, but the math sometimes can get very very heavy.
Yeah,
And
I don't think so. I don't think so. I think Monojit, right? Yeah,
yeah,
it's that heavy. I think you can go through the lectures. I think it will be explained
yeah.
very nicely. If you don't understand, keep reading it, and if you still don't understand, yeah, you can ask me here. I'll try to answer in the immediate week. If not, I'll record it and I'll remember your question and answer the next week for sure.
So you take this session only on Saturday 4 to 6, right?
Saturday 4 to 6. Typically, it don't last till 6 unless there is a lot of material to cover, because this time it was simple things, right? CNN architecture based. So I think it got
Yeah.
over quickly. Otherwise, yeah, probably on GANs or VAs, I think we can spend a lot of time. It may go till
Can you answer
6.
one
Yeah.
question regarding regularization, L2 regularization?
Yeah, please.
So I understand the basic what happens, what regularization does, L21, that I use eigen decomposition
Okay.
to scale the weight values, right? Like the weights which do not contribute significantly, they decay out due to eigen decomposition. So like I understand that, but still I don't understand like why that works actually.
Oh, why that works? Okay, it's very simple. Intuitively, I'll explain. Okay. Um. So, what happens is, let's say, overfitting and all those things, right? That's
Yeah.
what it does, right? Basically,
Mhm.
let's say I give you a class of uh, ResNets, ResNet, ResNet models, all ResNet models. Let's say that means it includes ResNet 18, 34, 56, or whatever, right? Some huge class. Or let's say only ResNet 110, right? And how many possible models this can have? And let's call this as set H hypothesis class, a set of all my possible ResNet 110 models. I don't know 110 exists or not, but let's assume let's ResNet 110 have, but how many possible models it can have,
110 means
right?
110 years.
10 layers, yeah. How many possible models we can have? I think we're complicating this. Let's forget even ResNets. I think we just have a simple linear model. Okay, even
Okay,
in
yeah.
this context also we can answer this. We are solving a regression problem. Okay, now my H is set of all possible W's, right? These are all my possible models are there, right? Now, I can fit any, I mean, I can fit the data uh, from so many possible models, right? If I allow W to take real numbers, is uncountably infinite, right? So infinitely many W's are possible.
So
But
many
by
W's will fit the data. Like, is it not unique? W is supposed to be unique, right?
W is supposed to be unique post optimization, right? Before optimization, what is the choice of W that you can pick,
Okay.
right? That is indefinite, right? W can be anything.
Okay.
So what happens if I impose W square, norm W square to be less than 1? So let's say this is my two-dimensional. Let's visualize W's, right? Earlier, my W choice of W is my entire plane, right? 2D plane.
Yeah.
Now what happens if I reduce my W? I allow my model to only pick W's within this circle.
So I've constrained the model.
Exactly. By constraining the model, you are reducing the overfitting. That's the intuition of
Yeah, yeah,
any regularizer, right?
yeah, yeah. No,
Yeah.
this one I understood.
Yeah.
When in the course, it
Yeah.
was expanded, right? So we did eigen decomposition to understand what actually L2 regularization was doing.
Okay. Okay.
Yeah, I wanted to understand that formula, after decomposing what it does to W. So what I know is we change the basis. From that, we scale the weights along particular eigenvalues, and then we
Okay.
again change back to our original basis. That one.
Actually, I'm currently exactly not aware of what you are talking. So W is something is like this, right? Uh, X transpose X whole inverse X transpose Y. Yeah. From there, what you are saying, you tell me. Let's try to do.
Not, no, no, not this formula. One second, I will.
And there will be some I
I'll
term here, of course, plus I, lambda times
one
I.
second. I'll check.
Yeah.
I'll check. Yeah, lambda times I something was there. One
Yeah.
second. I'll check it.
Yeah.
Uh, I got it. Is there any? It is actually your. Okay. Is there any possibility to share my screen?
Um,
I think I can. Right.
Let me stop sharing the screen. I've stopped sharing the screen. You can share.
Okay. Sure. can you see my screen?
Not yet. Yeah, I can see. Yeah. Oh, this is the deep learning textbook. Okay.
Hello.
Yeah. Tell me. Yeah. I can see your screen.
Hello.
Hello. I can see your screen.
Hello. Hello. Okay. This formula I was talking about. I can't hear you actually. So
Okay.
this formula.
Okay.
So actually we're using eigen decomposition. So this is the Hessian matrix. So from that we use this eigen decomposition, this formula.
Okay.
Actually, I can't hear you.
Just give me a second. Can you hear me now? Hello. Can you hear me now? Can you hear me now? Hello. Can you hear me now? Can you hear me now?
I can't hear you.
Can you hear me?
Hello.
Okay. Can you hear me? Can you hear me? Hello. Can you hear me now?
I can't hear you. Hello.
Now can you hear
I
me?
can't hear you.
Um, yeah. Can you hear me now?
Hello. I still can't hear you.
Hello. Can you hear me now? Can you hear me? Hello. Can you hear me? Hello. Hello.
Hello.
Yeah. Can you hear me? Can you hear me now? Hello.
Hello. Sure. I'll share my screen then. 1 second. So I think you can see my screen. So actually, I'm talking about this formula. So we have this Hessian matrix, which we, eigen decomposition, and then we get to this formula, this one. Yeah. Let's see if I can copy and paste it for you. Oh, I can't paste it. Yes, quadratic problem. Yes, true. So same time, right? Saturday 4 to 6.